Hello. Today, my group and I will be discussing an analysis of three-dimensional lift and drag on cambered airfoils in a 4x4 wind tunnel. My name is Andrew Watson, and I will be introducing this experiment. Inside a 4x4 wind tunnel, three-dimensional wing models, also known as cambered plates, were tested at various angles of attack, and the drag and lift were recorded. Also, a three-blade wind tunnel fan was tested as well. Of the three plates, one had no camber, the second had a camber very similar to that of the three-blade fan, and the third had the highest possible camber of the plates available for testing. Now, our objective of this experiment was to derive the three-dimensional lift and drag force coefficients of the wing models as a function of angle of attack. In order to do this, we first derived the dynamic pressure, which was calculated using the velocity and density of the flow inside the wind tunnel. Now, using the measured area of the plates, the recorded data for lift and drag, and the dynamic pressure we found in the first equation, we derive the three-dimensional lift and drag coefficients seen in equations 2 and 3. These equations allow us to plot and analyze our recorded data and determine the relationship between these 3D force coefficients and angle of attack. Now I will pass it on to Gabby to describe in more detail the exact procedure of this experiment.
Hi, my name is Gabby, and I'm going to be talking about the procedure part of our experiment. So the first piece of equipment we used was this three-blade wind tunnel fan because we were trying to predict the performance of this fan. So first we just measured the dimensions of the fan. Next, we found velocity, Reynolds number, and the expected force of the fan at several different points along it. The first point was the root, which is the center of rotation in the middle. The next point was just the middle of the blades of the fan, and then the last point was the tip of the blades. And for context, the Reynolds number is just a unitless aerodynamic number that tells us about the airflow. And as we expected, we found that all three of these values increased as you go outward on the fan. To find these, we actually also needed some information about the 3D wind test models we used. So we were provided with 5 different wings, and we measured the dimensions of each of these wings first. As you can see from this table, as you go from wing 1 to wing 5, the camber increases. And camber just describes the curvature of the wing. If you compare it to the length of the wing or the chord, you can find this value called percent camber. And so the values we found for that are in the bottom of this table for each of the wings. So for this experiment, we had to pick 2 wings we wanted to actually test. So the first wing we chose was wing 3, and this was because the percent camber of wing 3 was closest to the percent camber for the fan, which is 5.3%. We also knew going in that we would be provided with some data from a test of wing 1, which has 0% camber. So because of this, we also decided to test wing 5 because it has the largest percent camber, and we wanted to analyze that wide range of camber and how it affects performance. We chose a velocity of 70 feet per second because the wind tunnel had a max of 80 feet per second. So this was in that range, but it also closely matched the fan blade velocity at the root, which we found earlier. For angles of attack, we used a range of negative 20 degrees to 20 degrees in increments of 5 degrees, except between 15 to 20 degrees where we used increments of 1 degree because we expected this range would be where the wings might stall, and we wanted more data for that point. So we tested each wing in this 4x4 foot wind tunnel, and we had to first install it onto the 5-component balance shown in this photo. And basically this balance just measures lift, drag, and pitch for the wing. And all of that data is collected using LabVIEW. So we tested wing 3 and wing 5 separately. We installed them into the wind tunnel, tested them at all the angles of attack we wanted to, and then we generated a lot of data that we could then process and analyze the aerodynamic performance. So now I'm going to pass it on to Joe to talk about our results.
Thank you, Gabby, for explaining how this experiment was done and how we did it. I will now go over the results and discuss what they mean, what the graphs mean, and the implications they have on future experimentation. We're going to start with the raw lift and drag data plotted against angle of attack, with also the tar effect on it, which is the system load cell that holds the airfoil in place inside the air tunnel while we are conducting this experiment. And those will all be compared to previously established data of wing 1 with 0 camber that was already made by Dr. Rick called the RRA data. Then I will go over the non-dimensionalized quantities of the lift and drag, which are their coefficients. and they're plotted against the same angles of attack. This time the tar is not included in the graph, and they are both compared to the Wing 1 RRA data. Lastly, I will be talking about the coefficients of lift and drag that are recommended based on measured camber of an airfoil fan blade that is used within the fan. To start off with the lift and drag raw data plotted against angle of attack, you will notice that the RRA data is higher in total lift compared to the Wing 3 data. Whenever we would expect Wing 3 to have a higher total lift because it has uh, non-zero camber, which will generate more lift. But that is not the case here because the RA data was ran at a velocity of 80 feet per second, while we ran our experiments for Wing 3 and Wing 5 at 70 feet per second, and lift is proportional to velocity squared, signifying that discontinuity on why the RA data is higher compared to Wing 3. But both tests do follow the same trends for lift and drag compared to the RA Wing 1 data, which still is very good, and it signifies that there's high repeatability within these testing. And the equations that are equipped with these graphs both subtract the tar out from the equations and calculate the actual fixed coefficients of lift and drag, as well as the fixed lift and drag numbers. Next, with the coefficient of lift and drag, the outcome is more reasonable this time, with wing 1 being the lowest coefficient of lift and wing 5, which is the highest camber of 9.7% camber, having the highest coefficient of lift. And that is why normalizing the data will help show the trends more accurately than non well than dimensional quantities. And wings just with a higher camber percentage will generate more lift than those with zero camber. And as said earlier, these results indicate high repeatability across multiple runs and at different speeds. Lastly, with the recommended coefficients of lift and drag, this was based on a target fan of a measured camber of 5.3%, with it being slightly higher than the Wing 3 experimental data, which makes sense because Wing 3 had 5.2% camber. So the data was interpolated to be around there, but still higher. And this data supports predictable lift generation, making it well suited for future applications and allowing us to have a better insight on lift generation of these kind of airfoils. Now I will let Robert take over that conclusion and throughout this experiment.
Hello, my name is Robert, and I'm going to conclude this presentation by talking about our primary objectives, how well we achieved them, the 5 most important values for this experiment, difficulties encountered, experiment repeatability, and suggestions for future work. The 2 primary objectives in this experiment were to find a relationship between the 3-dimensional coefficients for lift and drag, labeled CL and CD, versus the angle of attack, labeled alpha. These were sufficiently met by testing the airfoils from a range of -20 to +20 degrees, and calculating our lift and drag at each angle using the raw data collected. These relationships were successfully graphed for each wing shape that we chose. We hypothesized that airfoils with larger amounts of camber would generate greater lift due to the steeper angle the air travels over the wing. This held true for the experiment for the 0 camber RRA airfoil, the 4.5% camber airfoil, and the 9.8% cambered airfoil. Labeled below are the 5 most important values from this experiment, which include Wing 5's maximum CL of 1.2, Wing 3's maximum CL of 1.04, and the recommended airfoil max CL of 1.09. The maximum lift force of Wing 5 was found to be 4.47 pounds, and the angle of attack that had the lowest drag for every airfoil was found to be 0 degrees. Some difficulties in conducting this experiment include measuring the camber values and tilt angle of the airfoil. We used a standard ruler to measure these values, and it was difficult to gather precise and accurate data this way. Another possible source of inaccuracy comes from the flutter at extreme angles of attack, which is shown in this video here. Error comes since the flutter of the wing can lead to losses in aerodynamic efficiency due to the increased drag and decreased lift. Even with sources of error,
The results and generated trends found in this experiment are likely easily repeatable by other experimenters due to the normalizations done to create lift and drag coefficients. To negate problems discussed earlier, future work should include improving the process and tools used for measuring the airfoils, and methods should be used if possible to limit the rocking or flutter of the airfoil under extreme angles. Thank you for your time and attention. Here's a slide outlining the work done by each member.